I want to share with you a topic that we've talked about previously. I want to talk about bitemporality. When we're talking about storing our data, one of the things that we have to take into account is whether that data may change over time. A very common problem that we have when we're trying to give people confidence in the reports we have is to say, this value is a consequence of this process. That's what provenance is all about, saying this line number that you see here is the aggregation of all of these coming up, and this is how the parsing worked, and I can tell you exactly why you see this number here. Well, one dimension that's not generally captured by provenance as we talk about it here is the temporal dimension, the time dimension. Think about this. Let's say we have some data in a database, some names and some values, and we want to perform some computation on this. Here we can select them out, or we could say something like select sum of value from data, or sum of, and if I can get this right, sum of, oh, let's get our other comments format. There we go. Or, there we go. Or we want to do something like compute the mean or average of that value. Well, one of the things that we might find ourselves in the circumstance of justifying is, I ran this report on Thursday, and I ran the report again on Friday, and the value changed. Can you tell me why it changed? When we write better reports, it's not just about reducing churn in the code that we write. It's also about reducing churn in the requests that come from our end users who are like, not quite sure that's giving me the right answer. Because when you really think about it, any report that performs an aggregation requires some faith. It requires some trust that the one number that you see is reliable without giving you insight into all of the constituent pieces of data that gave you that number. And if you're not sure that that's right, then you say, oh, maybe I want to decompose this. Maybe I want to do the roll up and roll down. You're just constantly spot checking this. Bitemporality is one of these superpowers that allows you to give people great confidence in your report in a very similar way that provenance does, but across a temporal dimension. And where the temporal dimension comes in is, what if this data changes over time? So here you can see we have the removal of one of the entities of our data. And if you think about this happening before and after a report was run, somebody might say, well, hold on a second. When I ran the report on Friday, it gave me A, B, C, D, E, F, and X, Y, Z. And when I ran the report again, it only gave me A, B, C, X, Y, and X, Y, Z. What happened to D, E, F? And you've thrown away that information. You threw away the information that that record was originally there, and now it was removed by some human process. So what you might do is you might add like an active flag. Now, of course, your preservation of data does have some legal requirements associated with it, and things like this may or may not be GDPR friendly, and there may be some additional approaches you have to take to satisfy those. But if we're accepting ourselves from all of that, we're talking about just data we own, data we control, the simplest way to address this would be to add some active flag, and then when we want to mark something as no longer being there, we set the active flag to false, which then allows us to perform our query. We have to add a little bit of a where clause here just to find the active rows. And when somebody says, well, what happened to DEF? You say, oh, notice this is no longer active. That's why. But there's not enough information here because they might be curious, why is it no longer active? Is it the case that it's no longer active because somebody removed it, and when did they remove it, and when was it no longer active? So you might say, let's make this modeling a little bit richer. What we'll do is we'll put a timestamp or a timestamp range here, and we'll mark when this record is active from. So instead of setting an active flag to false, what we'll do is we'll set the upper bound of when the record is valid for to some time, and if it's not, it's set to null. And what you could think is we either kind of select from an open-ended range or we select from a closed range, and here we can kind of see when this record was active from. Well, this is leading us down the direction of something very important. Even when we're working with data that doesn't have a natural time dimension, just entities that exist, and there's not really a, this was marked against this timestamp and this timestamp, there's a notion of the observed time. Every data set has, at minimum, one temporal dimension. And that one temporal dimension is when the database knew of that fact and when that fact was valid for. Very similar to this active flag. This active flag is saying this fact was known by this database as of this time up to this other time. And if the data itself has a temporal dimension, for example, this is time series data, you have sales for a company per quarter, per day, whatever the case may be, there's a natural time dimension, the date that the data actually refers to, and a secondary time dimension, the date when we knew that fact. One of the classical examples that I like to bring up when we talk about bitemporality is it is very common in just our everyday lives that we hear of and we react to bitemporal data sets that have 2 times associated with them. At minimum, 1 natural time and 1 knowledge time, 1 observed time, 1 system time. They're all synonyms for the same thing. Every so often, you hear the government released the jobs report for February. It said 50,000 jobs were created. The next month, the government released the jobs report for March. 75,000 jobs were created. And they revised the job report for February. It was actually 55,000 jobs that were created. Note that this data has a natural time dimension, which month the job report is for. And it has an observed time dimension, when you knew of that fact. That observed time dimension suggests that this data has ahistorical updates, which is very common for real data sets. For the jobs report, well, there's some data collection process that's in a rush to get published by the end of the month, and then some longer-term data collection process, which allows them to revise the previous numbers because they have a little bit more time, a little bit more leeway to collect a little bit more information. When the ahistorical update is made, when we're after March, but we're revising the data for March, well, we have that observed time. And you can easily think that somebody made a decision based off of the first knowledge time, and then they're revisiting that decision based off of the additional information. And those decisions don't take them in the same direction. They don't tell them to do the same thing. 50,000 was not enough to make a decision, but 55,000 was. And your system, if it doesn't record the knowledge time, it will not be able to reconstruct any past state of the report, and so you'll never be able to give somebody confidence as to why the numbers in that report keep bouncing around as ahistorical updates are made. However, if you were to record this active time, then you could say, oh, the reason why the report looks different today is because there was an ahistorical update that was made at the beginning of the month when they revised the figures when somebody changed this data feed. In my general experience, almost every data feed that claims to be immutable and write-only has some weird corner case where some legal entity, where some authority comes in and says, well, actually, we have to revise that. There are very few actually properly immutable data sets, especially considering that there could be mistakes in the collection process. So even if the data set is correct, maybe the collection process was wrong and you need to revise the numbers because you fixed the collection process. So given all of that, almost every data set I've ever worked with had at least 1 temporal dimension of the knowledge time because there was always some possibility that somebody has to go and revise it. Let me show you how we model this in Postgres. In Postgres, we actually have extensions that allow us to model the knowledge time very conveniently. Here you can see one called temporal tables, and what it does is it adds a column with the sys period, which is, you could think, basically our active time. It adds a temporary table, or it adds a table with the history of all of the previous records and adds a trigger. And what happens is every time we make a modification to the table, it takes the original record and puts it into our history table and updates the knowledge time of the record that's in our table. One of the consequences of the kind of active equals true false modeling is our table becomes append only. It becomes insert only. We can never delete anything, so the table grows without bound. But one of the nice things about these temporal table extensions, and databases like MariaDB have temporal support built into them. Postgres, you need an extension for it. One of the nice things is it actually keeps your queries really simple. It's a superpower in that it not only simplifies the queries, but it also improves the amount of information that you have to reconstruct any past state of the report. And here, what you can see is if we had our original data, and then we did an update, and then we query this data again, you can see we only see the active records. We only see what the updated value was. Let me multiply this times a large number just so you can see that very visibly. But as a consequence of storing this temporal information, we also have an audit table that tells us exactly when this value changed. And one small thing that would be nice to add to this is maybe a memo field that tells us why it changed. This changed as a consequence of this revision. Here's a link to more information so you could even track back why this changed. These ideas that we've shared with you are not isolated ideas. As you can see, they naturally interrelate. A good report is one that observes and preserves modalities because we know somebody's going to want to make a different choice later. That tries to reduce entropic loss of information until the very end. That tries to reduce entropic loss of information by, for example, modeling the underlying temporal dimension of the data bitemporally or fully temporally if there's only one temporal dimension. That tries to reduce the entropic loss of information by ensuring that there's provenance of whatever the reported data is back to whatever the source data is and all the steps in between. That tries to model the intentionality of what each of those steps are alongside that provenance, and that tries to make sure that at every step along the way, we have visibility into what is happening and what is going to happen next, so that when we have this report and somebody asks us, are you sure that report is correct? Are you sure that the value is this? Why did this value change? Why does this look the way it does? You can answer for them confidently and clearly. And when they say, great, but I want to make a different decision, or I want to look at this data very slightly differently, or look at another aspect of this data, another aggregation, another filtering, you can easily amend your report to include that without having to churn your code, without having to go back and rewrite everything from scratch. In this session, our goal was to give you some guidances, some framework for thinking through how to write better reports. I hope we have succeeded.